then transfer that to the ball mill, right? And once we finish the ball milling, we get most of the time we get some nice powder. Sometimes we don't get anything, right? It depends on the material we're using. Once we get the powder, we can use that in different methods. We can use that powder to consolidate some pellets, look at the corrosion performance. We can do sintering on those. We can do a spark plasma sintering. Most recently, we have been doing some cold spray and things like that, right? So we can do a number of things, but let's see what the properties it would be. So we looked at huge kind of number of binding alloys. I think right now I've just listed 15 here. We looked at around 20-25 binding alloying elements, binary alloys. And in each case, we are adding 5 atomic percent of vanadium or 5 atomic percent of the solute, right? And we also look at some commercial alloys. So we ball milled these alloys, and ball milling parameters were fixed. So let's not get in those details. So you can see in our publications, all these details are given. So this is some examples of how the microstructure looks like. So this is aluminum, chromium, manganese, moly, and all these alloys. So after ball milling, what we see is basically this is really refined microstructure. So you see here, the length scale is 2 microns. So we see some of the particles present, for example, in chromium, manganese, and moly, but they're really, really fine. And in some cases like vanadium, nickel, we don't even see them. Now, if we do some EDX analysis, what we see is that all these elements which we adding, they are like present in that interaction volume. So that tells us like all these particles are really mixed very well. At least they are mixed at some micron scale. I see some hands up. Do you have any question, or can you see everything fine? Anyway, all right. So, so you see really fine, kind of fine microstructure of milling. And if I'm doing casting, you can see this microstructure will be really, really coarse. We find, of course, intermetallics. Anyway, so I think see some. Can you still see? Okay, all right. I can see some issues. Can you still see my slides? All right, I'll keep going. I hope everything is fine. So this is so when we're doing this SEM, we saw that really very well mixing of the solute elements. Now, if we do some X-ray diffraction analysis, we can really calculate what the grain size is and what's the grain size and what is the solubility of these. I again lost my slides. Can you still see the slides? All right. All right, I'm uploading my slides. So what I'll do is actually when the slides are getting uploaded, I'll probably keep talking just to be in time. So if you remember, yeah, I'm sharing. It's taking some time to get them up. Yeah. So while the files are uploading, I'll just kind of give you the give you the background information there. So far we have been talking about this ball mill binary aluminum alloys, right? So the main thing is that once we do SEM, we saw that these solute elements were uniformly distributed. Doing XRD, we can kind of calculate the solid solubility, and we found like really high solid solubility. We found the grain refinement below 100 nanometers. So all the alloys we produced, they were really nanocrystalline structure, and the solubility of the alloying elements was much higher than whatever you predict from the phase diagrams. So I'll show that in a minute, but say, for example, in vanadium, the solid solubility was around 3.5 atomic percent, which is like 10 to the power 7 times higher than whatever you could get in the equilibrium conditions. All right, so my slides are here. I'll just skip a few slides just to, and probably I'll skip a few slides in and make my presentation a little shorter. To all right, all right. So So I'll skip a few of them. And all right. So over here you can see this grain size and atomic percent in solid solution for all these alloys we made. So if you look at this, the blue bars, you can see that the solubility, for example, somewhere so vanadium is here, right? So the solid solubility side is is by the green bar. So solid solubility is really high. If I look at the equilibrium solid solubility at the room temperature, it's really negligible. So we're getting like 10 to the power 7 times more solid solubility, right? Now, if you look at the properties, if you look at the hardness of these alloys is like somewhere here, 280 RPM, the 280 Vickers hardness for aluminum moly. So it's really high hardness. If I look at 5083 or 7075 aluminum alloy, they exist somewhere here. So the hardness of these alloys is kind of 2-3 times higher, depending on the composition, is 2 to 3 times higher than whatever you get, right? And we further look into strengthening mechanisms and so on, and we found that solid solution strengthening contribution was pretty high. So this is the strength for 7075 T651, which is the high strength aluminum alloy we use. So these alloys are much higher than have much higher strength than any other commercial alloys, right? So I'll probably skip that. I just wanted to give you introduction about the corrosion performance. So here is the corrosion performance, how that looks like. So here on the y-axis, you see the potential, and we basically presenting two potentials. One is the pitting potential, and another is transition potential, right? So what you can understand is higher. What we want is higher pitting potential and higher transition potential. Higher these numbers are, higher the corrosion resistance would be, right? So here, if you look at these numbers for these alloys we made versus pure aluminum here. So sorry. So if I look at pure aluminum, this is my pure commercial alloy. And remember, the pure aluminum is more corrosion resistant than any other commercial alloys, right? So if my alloys are more corrosion resistant than pure aluminum, that means they are more corrosion resistant than any other commercial alloys, right? So that's why we're comparing this from pure aluminum. So now if I compare the pure aluminum with the ball mill, the nanocrystalline pure aluminum, we don't see huge difference. We see slight increase in the pitting potential, but the transition potential really decreases. So it's really hard to compare these two, really hard to say which one has better corrosion resistance. So I would say they have the pretty similar corrosion resistance. And what does that mean is basically grain refinement does not have huge impact on the corrosion performance, right? But now if I look at this aluminum, moly, vanadium, and all these alloys, you see huge increase in the pitting potential and the transition potentials. They are really corrosion resistant, right? And this corrosion resistance is coming just because of the change in the composition and the way we kind of designing the microstructure. Now, if you look at the immersion test data, this electrochemical data kind of tells us some short-term electrochemical test, right? So they gives us good indication of the corrosion performance, but we really wanted to see what happens if we immerse this material for a long time. We put them in service condition, what could happen. So what we did was we put these alloys in the salt water and we measured the change in the pit size and pit depth for 6 months. And now if I compare my commercial alloys, and we have chosen these commercial alloys are really corrosion resistant one, not the one like 7075 that would have like huge pit depth. And if I compare those with our ball mill alloys, the ball mill alloys has really low pit depth, right? So basically they didn't corrode much. So the pit depth was like around 500 nanometer or something after around 6 months. So really corrosion resistant, and we kind of look into different other electrochemical properties, and we kind of confirm they're really good, really corrosion resistant. Now, if you recall, initially we were talking about corrosion resistance as a function of hardness or strength. So here is the pitting potential, which is the measure of the corrosion resistance. Higher the number, higher the corrosion resistance would be, right? So these alloys here, these are the alloys we develop in our lab, and these are the commercial alloys here, right? So you see in commercial alloys, you're increasing the strength, you're decreasing corrosion performance, but the alloys we made, these ball mill alloys, they really have huge corrosion resistance and the strength, right? So somewhere in this region. So what we understand from here that, well, we can design these alloys with the high corrosion resistance and high strength, right? So that's not a problem. And if we want to further increase the strength, of course we can do a lot more work. We can change the composition and so on. But we wanted to stop here and wanted to see, well, what would the best strategy to further increase the corrosion resistance, use them in real life, understand what happens. So I guess in order to further design these alloys, we really need to understand and answer some really hard questions, right? We really need to know the key corrosion mechanisms. I mean, of course, we know that we define the microstructure, we know that we get high solubility, and all these factors are contributing to the corrosion resistance. But how exactly, say, increase in the solid solubility would influence the corrosion mechanism, right? So these kind of the difficult questions we wanted to answer, right? What would be the thermal stability? What would be the effect of compositions, underlying content? What would be the formability? There are a huge number of these questions, around. So of course, I mean, it takes time, and we cannot answer all the questions. But we started looking at a few things. We looked at the influence of heat treatments, see the thermal stability. What we found was aluminum vanadium is really thermally stable. I'm probably skipping this slide. I'm not kind of going through everything given the time I have. I'll try to like finish in the next 10-15 minutes, so I'll probably skip that part. But if someone is interested, I could talk about that later on. But these alloys were really thermally stable, and thermally stable means if you go to up to 300 degrees centigrade, we don't see significant grain growth, and we don't see significant loss in solid solubility, right? So these two parameters are very important. And aluminum vanadium alloys was also responding to the age hardening, right? Now, if you look at the alloying content, I mean, we look at pure aluminum to all the way up to aluminum 20 atomic percent alloys, and these are just SEM images. What we see is if we increase the alloying content, basically we start seeing huge increase in the solid solubility of the alloys. We see huge decrease in the grain size. So for pure aluminum, grain refinement was somewhere like around 90 nanometer. Here with the 20 atomic percent, we going all the way to like 18 or atomic percent. We also have huge increase in the solid solubility as we increase in the alloying content. And if you look at the properties, you can see the Vickers hardness here. That's plotted for these different kind of alloys we made. We can get really high Vickers hardness, high potential, pitting potential, and this is kind of the summary of everything we have. So if you look at this blue curve now, these are alloys with high alloying content, and they have some different kind of processing, and we can get really like hardness up to 500 Vickers hardness, huge pitting potential close to some of the stainless steel. Now over here we see that, well, all this high strength and all that we can get, and really coming from the grain refinement, coming from extended solid solubility of the alloying elements, and a lot of other parameters we really don't know, but they could be contributing. There would be, say, incorporation of oxygen or argon that is present in the milling media, dispersion of unalloyed particles, and so on. So answer all those questions, we kind of sit back and start thinking what could be the corrosion mechanism. So you can find in some of our earlier paper and some of the recent papers where we have proposed some of these mechanisms, and we started looking into kind of start validating them, or started looking at if they are valid or not. So some of the proposed mechanism was that enrichment of the passive film with the alloying elements. So say for example, I'm taking, say, aluminum chromium and aluminum vanadium. What could happen is the passive film, the surface film which is forming, rather than being aluminum oxide, it could be, say, vanadium oxide or chromium oxide. So that's one possibility we have. Then we can also have the possibility that we can have the increase the repassivation. So we know that pitting corrosion is the phenomena where you have passive film breakdown and repassivation. Now, if repassivation or healing of this the corroded material is faster than the pitting, what would happen is basically, even if you break down the passive film, it will reheal immediately, right? And in that process, basically you see high corrosion resistance rather than having pitting. I think I lost this the presentation again. I'll upload the slides again. All right, while the presentation is uploading, what I'll do is I'll uh, there's some issues in uploading now. All right, so it's uploading. So what we did is basically we kind of look into this various mechanisms we thought about what could be the possibilities, and we started testing all these different hypotheses one by one, right? So so one possibility was that you have this surface film which is just made of the solute element, and you'll see that very soon we learned that's not the mechanism, and I mean it could happen in certain conditions, but not in every single condition. Then we started looking at that it could be possibility that the solute elements are somehow increasing the depressivation tendency. Then the third was the, if you recall the kind of fundamentals for happens because of the presence of the secondary phase particles. So for example, iron present in aluminum causes lots of corrosion. And the mechanism is that this iron that acts as a cathodic particle, right? And that causes the corrosion. Now, somehow we can prevent this cathodic activity of iron. We can basically increase the corrosion resistance, right? So very soon you'll see that some of the compositions we can choose where this cathodic activity of iron could be controlled, or cathodic activity for any cathodic particle could be controlled, right? And if you shut down that cathodic activity, we could basically repassivate our material, right? Another possibility we were thinking about was if we choosing the solute element wisely, or some of the solute elements, uh, when they corrode, they can release the species which are corrosion inhibitors. So you can think about, rather than adding corrosion inhibitors in the stream, in the environment, you can just have the corrosion inhibitor within the material, and that's kind of causing all the repassivation, right? So what I'll do is I'll bring back, I'll skip some slides, so I don't want this to happen one more time. So I was somewhere here on this slide. Okay. So these are the mechanisms I was talking about when I lost these slides. All right, so what we started doing, we basically started looking all these mechanisms. So what we do is X-ray photoelectron spectroscopy and started looking at the surface film. And what we look at basically solute to aluminum ratio, right? So if that's kind of more than what we adding, then we can think about that we are enriching our passive film. But in most of the material, like you can see vanadium, niobium, molybdenum, chromium, most of them we see that there is no actually real enrichment. So our first hypothesis is that we're forming the exclusive solute-rich passive film. That seems not working, right? So what we started looking at was like, well, we did lots of surface film characterization by XPS, SIMS, and I'm not presenting all these details, but what we learned is that these materials are really, really heterogeneous, right? So we thought, well, can we just characterize the surface film wherever we want? And we wanted a technique which has really high depth resolution and high lateral resolution. So also XPS and SIMS, they give really high depth resolution, but they lack in lateral resolution, right? And we cannot just kind of focus on the point we want. And our resolution, lateral resolution, means literally we want a few nanometers lateral resolutions, right? So we thought of using the TM, right, which is not really conventionally used for studying all these surface forms. So what we did is we kind of make our sample. So you can think this is the sample after some immersion time, or we can do a bunch of electrochemical tests and make our surfaces. We take them to the focus ion beam, and we really make the focus, and then we can make the TM samples wherever we want, right? So what we do is, this is an example where we have this sample after immersion. You can see this CM image here. We choose a region which we want to analyze. Then we deposit platinum on it. So once you deposit platinum, you start doing trenching on both sides. And then we make this lift out, fib lift out, put that sample on the TM grade, fib grade, and then we thin it down to less than 100 nanometers. So the advantage of this technique is now you can see the top surface. This one was immersed in the material, or this one was just after the corrosion test. And we can also see the substrate here. So we can actually characterize the surface film or corrosion products. and we can see the relationship between the substrate and the surface film or corrosion products forming, right? So we use that a lot. I'm just showing a few just examples. So one example, if you see this publication here very recently, so we have some examples there, and there is a lot more publications coming in on this these topics. So anyway, if I take this, so this is the air form surface. So we have this aluminum vanadium alloy. We didn't do any electrochemical test. We just kind of put that in air and then make this fib lift out and look in the TM. So you can see here this surface film was like 5.6 nanometer at this location. So this was varying from somewhere from 3 to 6 nanometer depending on the location. And then what we really learned is that if you look at this elemental distribution, I don't know if it is visible on the screen or not, we can start seeing the vanadium enrichment just beneath aluminum oxide. So our bicycle film is aluminum oxide, but just beneath that we have kind of enrichment of vanadium, right? Now there are some regions where we can start seeing pits. So this is a small pit, so it's really, like 200 nanometers, 300 nanometer thick pit. What was really interesting, if we look at iron and vanadium, so you see that pits are originating around iron, and if you look at vanadium, vanadium is kind of depositing on iron. And the same thing we look into, this is another example, which is just after 30 minutes immersion, and you can see this pit over here, really small pit. And this pit is forming basically around this iron rich particle. So this iron rich particle was there, and that was causing all this pitting corrosion. Now, if we look at iron, and we see the vanadium is depositing on iron, right? So somehow it's this deposition, we believe that's kind of shuts down the cathodic activity and causes the repatriation. Because if you compare these pits after say 30 minutes, after 2 days, after 6 months, they don't grow much. And in each case, we see this vanadium deposition. So it seems like this vanadium is really working very well in doing that. So with that, I would like to kind of summarize my talk. I mean, this is ongoing work, but what I wanted to tell you here is that we can really design these lightweight and really corrosion resistant alloys by designing this far from equilibrium microstructure. You just really need to choose a solute content which could prevent corrosion, and there are different mechanisms, right? So we looked at listed like those 4, 5, 6 proposed mechanisms. Look into that and find out which element can kind of act as an species to inhibit the corrosion as it initiates, right? And then you can look at the strengthening by solid solution or bright green refinement or both, right? And then you can really design these alloys. And so basically we have the microstructure, we have the compositions. We need to find the right techniques to upgrade them and use them properly, right? With that, I would conclude the talk, and I would like to thank all my students. So Javier was my student. A lot of work I presented here was done by him. Now he's a corrosion scientist in Ford Motors. Two of my students still working on these projects. They're finishing their PhD. A number of undergraduate students had opportunity to work on various aspects of these materials. I wanted to thank the collaborators with Army Research Lab and other universities who help in doing some of the processing, characterization, and so on, and ultimately the financial support from National Science Foundation. And with that, thank you very much. And if you have any questions, I'm here, and you can send me email. So I'm open for any question you have. Thank you. And I wanted to apologize again for all these technical issues.
Thank you so much, sir, for giving us your valuable time and sharing your experiences with us.
Thank you very much. Yeah.
Thank you so much, sir.
Thank you.
Participants, you can leave the meeting now. Okay. And the authors who are present here can go back to their respective tracks for their presentation. Thank you. Thank you all. You can leave the meeting now.